Welcome back everyone. In this lecture we are going to see the principle of inclusion and exclusion. So let us actually start with this basic question. So let us say we have a finite set capital X and then some subsets of that given capital X. So let us say X is a finite set and then we want this A1 etc. an. So they are actually subsets of capital X. We want to actually find the cardinality of this union AI. So that is the question. So the question is, what is the cardinality of union AI range from 1 to n. Okay, so let us actually look at some simple example. So then we will be able to understand how to find the cardinality of this given union A1 etc. an. So let us take only two sets. So let us take n equal to 2 and then look at the cardinality of A1 union A2. So let us say I have some element x in this union. So then what happens to the this x? So this x is, let us say it is in the union. So then this either this x actually belongs to A1 or this x actually belongs to A2. So this is what will happen because it is in the union. Now if we want to actually just use this observation to count the elements of A1 union A2, then the very first rough count will be, so the cardinality of A1 plus the cardinality of A2. So we just count all the elements in A1 and A2. But what is the problem with that? The problem with that, some elements x may be inside the intersection. So it can happen that, the element x may be inside the intersection. If it is in the intersection, then what happens? So then it will be counted twice in the sum cardinality of A1 plus cardinality of A2. So that we should take care. So we should just count it only once. So it means we should not actually count it twice. So we should just take out all the elements that are counted twice in this cardinality of A1 plus cardinality of A2. So that gives the formula for the cardinality of A1 union A2. So pictorially speaking, so we have this A1 and then we have this A2. So let us say this is A1 and then this is A2, then we have this A1 intersection A2. So now if you look at the union A1 union A2, so this can be written as A1 difference A1 intersection A2. So this is the part that is here. So I am only taking this part A1 difference A1 intersection A2. So then what we can do, we can take this union and then look at this part which is actually the intersection. So then it is A1 intersection A2. So then we can write it as union A2 difference A1 intersection A2. So this is this the third part which is here. So that means the cardinality of A1 union A2 is going to be, the cardinality of A1 union A2 is going to be the sum of these cardinalities, but then it is easy to see that this union is exactly the cardinality of A1. So what we have indeed, so this is exactly the cardinality of A1 plus, you can see that, so this is going to be the cardinality of A2 minus the cardinality of A1 intersection A2. So this is going to be the cardinality of A1 plus cardinality of A2. In this sum we have counted the elements of A1 intersection A2 twice, so we just subtract them. So this gives that the cardinality of A1 union A2 is exactly the sum of the cardinality of A minus the cardinality of the intersection. So this is what the principle of inclusion-exclusion, and this is something that we want to actually generalize to any given collection of finitely many subsets of capital X. So, indeed we want to prove the following theorem. So, let me just state the theorem. So, we want to count the cardinality of the union. So, let this A1 etc. AN, they are all subsets of capital X, and X is given to be finite set. So, now what we are interested in? We are interested in the cardinality of this union of A1 etc. AN. What is the cardinality of this? So, the argument that is presented here, that can be generalized to the following. So, we can actually take this very rough sum, which is the sum of the cardinality of AI. So, this is the first sum that one can actually expect, but problem with this sum. So, we may count some of the elements in many ways. So, for example, the elements that are in the intersection of two sets AI and AJ. So, that will be counted twice in this sum. So, that means those elements should be subtracted from this sum. So, we just subtract all the elements that are in the intersection of two sets. So, we just look at all possible intersection of AI intersection AJ, and then the elements in this intersection counted twice in this summation. So, we just subtract them from this sum. So, then we get some better approximation of this union of AI, but the thing is, this is not good enough, because the elements that are in the intersection of three sets, they are actually subtracted twice in this summation. So, basically the elements in the intersection, three intersection, they were actually kind of extracted from this summation. So, we have to add back the elements that are in the intersection of three sets. So, we have to just add back those elements which are in the intersection of three sets. So, we will have something like this, and then in this summation what we have done is we have again actually counted more time this elements that are in the intersection of four sets. So, that actually should be again subtracted back. So, then this actually process actually continues. So, this is what called the principle of inclusion and exclusion. So, let us actually make the precise statement and then prove it. Okay. So, basically what we have, so the union of this AI, I range from 1 to n, so which is given by the cardinality of this is given by this alternating sum, the summation the cardinality of AI, I ranging from 1 to n, minus the cardinality of A intersection AJ, where we choose any two sets from this collection AIs, and then we continue like this, plus etc. plus minus 1 power n plus 1, the cardinality of A1 intersection etc. intersection A. So, we can give actually multiple proof of this fact. So, one can use for example induction in order to prove this statement. So, we have already convinced ourselves that when we take a union of two sets, then the cardinality of A1 union A2 is given by this equation, cardinality A1 plus cardinality of A2 minus the cardinality of A1 intersection A2. So, now one can use this identity in order to prove the identity in general. So, for example, let me do the 3 case. So, if we take A1 intersection A1 union A2 union A3. So, then what we can do, we can actually club these two and then call it B1. So, then the cardinality of this is going to be the cardinality of B1 plus the cardinality of A3 minus the cardinality of B1 intersection A3. So, now what is the cardinality of B1? the cardinality of B1 is given by cardinality of A1 plus cardinality of A2 minus the cardinality of the intersection of A1 A2. So, now what is B1 intersection A3? So, this is going to be A1 intersection A3 union A2 intersection A3. So, that means the cardinality of B1 intersection A3 is going to be the cardinality of A1 intersection A3 plus the cardinality of A2 intersection A3, then minus the cardinality of intersection of these two, which will be A1 intersection A2 intersection A3. So, the cardinality of A1 intersection A2 intersection A3. So, if we plug in back in the original equation, so then what we are going to get? So, this will be replaced by cardinality of A1 plus cardinality of A2 minus the cardinality of A1 intersection A2, and then this will be replaced by minus the cardinality of A1 intersection A3 minus the cardinality of A2 intersection A3, and then plus the cardinality of A1 intersection A2 intersection A3. So, now you can go back to the original formula and then see that so we have exactly the same thing. So, the cardinality of A1 union A2 union A3 is given by the cardinality of A1 plus cardinality of A2 plus cardinality of A3 minus the cardinality of A1 intersection A2 minus the cardinality of A2 intersection A3 minus the cardinality of A1 intersection A3 plus the cardinality of A1 intersection A2 intersection A3. So, that is what we have it here. So, this way one can actually complete the proof inductively for this collection of finitely many AIs. So, now what I am going to do, I am going to actually give much more straightforward proof by counting the elements in both sides. So, let us actually look at some element x in the universal set. So, let x in capital X. So, now x actually belongs to, let us say some exactly r number of sets coming from this A1 etc. A_n. So, if x is not in the union, then it will not give any contribution to this union of A on the left side. So, this is my left hand side and this is my right hand side. So, if x is not in the union, then there is no contribution on the left side. So, similarly there is no contribution from the right side. So, we do not need to worry. So, we can actually assume that x is in the union of A, I range from 1 to n. So, now what we are going to say? We are going to say that x actually belongs exactly R of the sets from this A1 etc. A_n. So, just to be clear, let us label them as AI1 etc. AIR. So, this I1 etc. IR, they are all coming from 1 to n. So, these are all the collections where x is there. Okay. So, now we are going to actually count what happens to the right hand side. So, x is counted exactly using the following formula. So, since x actually belongs inside this AI1 etc. AIR, so we are going to say that on the right hand side x is counted exactly as R choose 1 minus R choose 2 plus R choose 3 minus etc. plus minus 1 power R plus 1 and R choose 2. So, this many number of times it is counted on the right hand side. Okay. So, let us prove this. So, this is our claim. So, how one actually proves this? So, let us look at the collection AI1 etc. AIR. So, now if we actually look at the singleton sets in which x appears. So, that will be one of this AI1 etc. AIR. So, that means x appears in exactly R choose 1 number of single sets. So, x appears exactly R choose 1 number of single sets, okay, because x has to come from one of this AI1 etc. AIR. So, now if we actually look at how many intersection of two sets x appears, then it is clear that x appears exactly R choose 2 pairwise intersections. Why? Because we can choose any two sets from this collection AI1 etc. AIR. So, then x will be in the intersection of them. So, namely x is in the intersection AI intersection AJ, where this IJ chosen from this I1 etc. IR. And similarly, we can continue this. So, for general K, which is less than or equal to R, what we can say? We can say that x appears exactly R choose K number of intersections of K sets. So, more generally one can say that x appears in exactly R choose K number of intersections of K sets. So, where this K sets intersection will come from? So, that will again come from this collection of I1 etc. IR. So, we choose any K number of sets from this AI1 etc. AIR, then it is clear that x appears in that intersection, and this is the only way it can appear in the intersection. So, that means the total contribution of x to the right hand side. So, therefore, the total contribution of x to the right hand side of the formula that is given in this theorem. So, that is exactly R choose 1 minus R choose 2 plus R choose 3 minus etc. plus minus 1 power R plus 1 R choose R. Okay. So, this is the contribution that we are getting. So, because x is actually the way we counted that actually tells you that the total number of contribution x to the right hand side is given by this. But what we know from binomial theorem, so we know that so if we actually take this summation minus 1 power k R choose k, where k is from 0 to R. So, this is going to give us exactly 1 minus 1 power R, which is 0. So, that means what we have is that this summation is exactly given by 1, because this is exactly 1 plus this star, sorry, minus minus of this star. So, that means the star should be equal to 1. So, therefore, every element in the union is exactly counted once. So, and every element outside the union is counted exactly 0 times. So, that means this proves that the formula that we have here in this theorem, that is correct. So, we wanted to count the cardinality of this union of AI, and then we have told that this right hand side exactly counts that the cardinality of the union. So, this actually proves this inclusion-exclusion principle, and like I said, one can actually prove this using induction as well. So, this is not very difficult thing to do. Okay, so now let us look at some example where we can actually apply this inclusion-exclusion principle. So, in some sense in almost all combinatorial problems, so one will be using this inclusion and exclusion, so even without explicitly mentioning that we are using it. So, for example, I am going to give you some very basic problem from number theory, and this actually kind of tells you that how to count integers between 1 to 100 that are divisible by, let us say, 2, 3 or 5. So, here is the problem. So, we want to count the number of integers between 1 to, let us say, 100, so such that this x is divisible by, let us say, 2, 3 or 5. Okay. So, this is what we want to count. So, let us use inclusion-exclusion principle to do this. So, for this, so we need to first find out the sets, correct sets that we are interested in counting, and it is clear that if we denote this a n by those x in G such that 1 less than or equal to x less than or equal to 100, where x is divisible by n. So, let us say n is 2, 3 and 5. Okay. So, then this set, let us call this is capital X, then this capital X is just a union of the intersection of these three, A2 intersection A3 intersection A5. Okay. So, now let us see how one can actually count this intersection. So, we already know how to actually okay. So, the intersection will be all the numbers that are divisible by all these three. So, we want actually x is divisible by either 2, 3 or 5. So, that means I am looking at only the union. So, then it is clear that the cardinality of x is given by the cardinality of A2 plus the cardinality of A3 plus the cardinality of A5 minus the cardinality of A2 intersection A3 minus the cardinality of A2 intersection A5 minus the cardinality of A2 intersection A3 intersection A5 plus the cardinality of A2 intersection A3 intersection A5. So, this is the formula that we are getting. So, which counts the cardinality of x, which are interested in counting. So, what will be A2? A2 is those numbers which are divisible by 2. So, that means all possible multiple of 2, and it is not very difficult to see that all multiples of 2 in between 1 to 100 will be just exactly 50, and similarly all multiple of 3 which is between 1 and 100. So, the multiple of 3 maximum it can go to 99. So, it will be 99 by 3 which is 333, and similarly the cardinality of A5 will be 20. And what is the cardinality of A2 intersection A3? So, since 2 and 3 are relatively prime, so the cardinality of A2 intersection A3 is exactly same as the cardinality of A6, because it should be divisible by 6, and all multiple of 3 will be the 100 divided by 6 this greatest integer function, which is exactly 16. And similarly, if you look at A2 intersection A5 which is A10, so the cardinality of A2 intersection A5 is going to be 100 divided by 10 which is 10. and similarly A3 intersection A5 will be A15. So, which is exactly given by the cardinality 100 divided by 15, the greatest integer, which is 6. So, what will be the intersection of 3, A2 intersection A3 A5, so which is exactly A30, the multiples of 30. So, it is going to be 100 divided by 30, so which is exactly 3. So, now if we plug in back and then calculate what will be the cardinality of x. So, then we can see that the cardinality of x is exactly given by 50 plus 33 plus 20 minus 16 minus 10 minus 6 plus 3. So, which is exactly 74. So, that means there are 74 numbers between 1 to 100 that will be either multiplied by 2 or 3 or 5. Okay. So, this actually kind of used in this very nice counting problem. So, similarly, it can be used in many other places. For example, especially all the countings involving permutations can be actually counted using inclusion exclusion. So, let us do one example. So, we can actually count the derangements. So, what is derangement of 1 to n? It is a permutation of 1 to n with no fixed points. So, derangement of 1 to n is a permutation with no fixed points. So, now what one can do, one can actually count the number of derangements. Let us denote this dn by the number of derangements of 1 to n. So, then we want to get a formula for this dn. So, using principle of inclusion exclusion, one can write down very explicit formula. So, for that let us see how one can actually precisely count all the derangements. So, to count all the derangements, first we need to actually understand the set of permutation that fixes something. So, let us denote this ai. So, this is the set of permutations such that sigma of I is I, and it is not hard to see the cardinality of ai will be just exactly n minus 1 factorial, because it fixes I, you are allowed to permute all other n minus 1 elements. So, now if we take this union, so that is going to be all the elements that has at least one fixed point. So, the union of ai, I ranging from 1 to n, is going to be the set of permutations that have at least one fixed point. So, that means if we are interested in counting the number of derangements of 1 to n, what we need to do is we need to count the cardinality of the complement of this union of ai inside the set of permutations, and it is not difficult to see. Okay. So, the dn is the cardinality of Sn difference the union of ai, I range from 1 to n. So, which means to get dn, so it is n factorial minus the cardinality of this union of ai, I range from 1 to n. So, this is what we need to count. So, let us actually count how the union of ai, and then see like how one can write down the explicit formula for dn. So, if we actually look at the union of ai, if we go back to the formula, so to count this union, we need to actually look at the intersections and then see what will be the cardinality of the intersections. So, let us do that. So, let us fix some capital S, which is subset of 1 to n. So, if S is subset of 1 to n, let us say the cardinality of S is k. So, then we are going to look at the intersection of this I comes from capital S. So, note that the elements of capital S, they are all fixed by the permutations in this intersection. So, that means all the elements that are outside the elements of S are allowed to permute whatever way we want. So, that means the cardinality of this is same as the cardinality of S difference this 1 to n difference capital S. So, which is exactly the cardinality of this n minus k number of elements, which is exactly n minus k factorial. So, the cardinality of the intersection is given by this. So, now if we plug in back in the formula that we are interested in, so we can see that so this dn is going to be exactly n factorial minus. So, then we can write down the formula as follows, which is the cardinality of the union of A, which is given by the summation minus 1 power the cardinality of S plus 1 intersection A I in S, the cardinality of this, where S is non-empty subset of this 1 to n. So, I have rewritten the formula, the original formula in this fashion, so that we will be able to actually just look at this summation. So, this is exactly the cardinality of this union. So, now we know already what is this intersection in this case. This intersection is exactly given by n minus k factorial, and how many S's are possible, you can actually choose n choose k S's are possible. So, that means the dn is given by n factorial minus summation k range from 1 to n and then minus 1 power k. So, we want to put this k plus 1 here because cardinality of S is k, and then you have exactly n choose k number of S's and then you have n minus k factorial, that is the cardinality. So, now if we rewrite this formula, so then you can see that this is exactly given by, so we can take so this n choose k is nothing but n factorial divided by k factorial times n minus k factorial. So, we can cancel out this n minus k factorial. So, then this becomes exactly minus 1 power k divided by k factorial, and then we can take out this n factorial out, where k ranges from 0 to n with the sign minus 1 power k. Okay, because this becomes plus and then this vanish. So, this gets vanished. Okay, so, that means we have this explicit formula dn is given by n factorial summation minus 1 power k divided by k factorial, k range from 0 to n. Okay, so, this actually tells that how one can apply inclusion-exclusion principle in order to get some closed formulas for the counting problems that one interested in. Unfortunately, inclusion-exclusion is always alternating formula. So, it does not give us any non-negative formulas. The coefficients are always alternating. So, that is one of the biggest disadvantages in using inclusion-exclusion. Okay, I will stop here. We will continue with Mobius inversion in the next class. Thank you. We will stop here.